The Electronic Alliance brings you another in a series of technical presentations to continually educate you in product design and manufacturing. Today's session is about embedded instrumentation trends, including the drive to non-intrusive board test. We welcome Adam Lee of Asset Intertech. Anytime you need to find a qualified source for your design and manufacturing needs, contact the Electronics Alliance.
As Gary said, we're going to talk about embedded instrumentation and how the trends there are driving towards non-intrusive board test. The emphasis being on less probes with more coverage. So we'll start with an intro to embedded instrumentation, look a little bit at the what, why, and how. Kind of the catchphrase that we use at Asset Intertech is that embedded instrumentation sees what the silicon sees. The basic idea being that embedded instrumentation is instruments that are embedded in silicon. More specifically, what is it? One definition I pulled from a report from Frost & Sullivan that you can access on the internet. But in a nutshell, embedded instruments are intellectual property blocks, what's often called IP, that are inserted within the chips to perform specific validation, test, and debug functions. The functions that are implemented can relate to the silicon validation and test, such as at the silicon suppliers, Texas Instruments, and the like. Or they can be used to functionally or structurally exercise the printed circuit boards on which the silicon resides, or in fact through an entire system. Boundary scan is an example of an embedded instrument that is deployed primarily for printed circuit board use. The instruments continuing from Frost & Sullivan range from your built-in oscilloscopes, logic analyzers, memory built-in self-test or BIST, power monitors and meters, temperature monitors, and so on. Again, we mentioned boundary scan in the printed circuit board context. We'll talk more obviously about other board level instruments being the focus of this talk. Typically, as of the time of the writing of the Frost & Sullivan article, they found that most of the instruments had only been exposed for silicon use. But increasingly, the instruments are being made available for board level use. Not only boundary scan, but the additional facilities such as, for example, pseudo-random bit streams and pattern checking for high-speed I/Os. Whereas those may have been predominantly made available for silicon validation, increasingly they're being made available for board users as well. One group that we follow closely at Asset and that I've had some involvement with is IEEE P1687, what's called IJTAG group. They define embedded instrumentation as any on-chip circuit for test, debug, diagnosis, monitoring, characterization, configuration, or functional use. Note here that they extend beyond the validation, test, and debug realm and extend into functions that are actually inherent to the mission in some cases. Essentially, 1687 defines those as any instruments that can be accessed or configured from or communicated with by an on-chip network described in ICL, which is the 1687 instrument connectivity language, and which in turn connects to an external device interface, the most common of which is the JTAG test access port. We'll talk more about that momentarily. They go on to amend that to say that an instrument in the 1687 context is typically a module that has only a client interface. In other words, it's a slave within the instrumentation network. What are some of the technology trends and challenges that we're facing? Of course, the abstract that mentioned Moore's Law, the cores are becoming ever more expansive and dense. The software that's involved is also growing in complexity. That leads to challenges for software debug as well as hardware validation. We have increasing use of SerDes, serializer, deserializer I/O, high-speed I/O, moving now well beyond the 5 gigabit per second range up into 10 gigabits per second and more. In that case, the challenge that arises is that the signal integrity validation or the system marginality validation can no longer be done by way of physical contact. You really have to see what the silicon sees because the probes can't. Even if you can probe, there's so much interference with the channel that you have to employ very high-end math for the de-embedding, and it all becomes muddy very quickly. Packaging technology, of course, is increasingly more integrated. We see a lot of ball grid arrays, of course, and ever more so we see stacked integrated circuits. Of course, there's also, besides the sort of system in package stacking that you see here, there's also package on package. I understand QC is pretty familiar with package on package. And of course, that sort of technology removes access that you need for design validation and for structural test. Of course, considering package on package, one of the common varieties that you see is memory on package, LPDDR3 and LPDDR4 coming on. And they're basically your memory stacked on top of your logic die, and there's no way to test it. There's no way to access it except through some sort of embedded instrumentation. So how does all of this impact test and measurement market? Of course, really it impacts it in two ways. The one is the possibilities for instrumentation are facilitated by the higher level of integration. You can take instruments that used to be in large boxes and now they're in modules, such as in a National Instruments rack through what they call their virtual instruments model. And increasingly the instruments are not in full modules but actually embedded on the integrated circuits themselves. Just like you had software to manage the traditional instruments, and you have the virtual instrumentation LabVIEW type products for virtual instruments, you also have a new range of tools that's available for the embedded instruments. On the other hand, of course, the technology trends require that the instrumentation become more proximate to the circuits to be tested. And again, so both of those trends give rise to embedded instrumentation. The need for embedded instrumentation is dictated, if you will, by Moore's law and the increasing density and complexity of the circuits, and of course the ability for those instruments to be embedded is facilitated by those same trends. All of this basically, as I somewhat alluded to, leads for a trend from hardware in the sort of tangible sense to a more of a software-based instrumentation. So of course there are circuits inside the ICs that provide the basic measurement capability, but you also need software that goes in and provides access to those instruments and allows you to control, access the information that the instruments have access to in the embedded environment. Some examples that are illustrated here, of course, is with the old style of logic analyzers or CPU emulation. You had external circuits that connected to your board, and they monitored or in the very old days emulated the operation of the microprocessor on your board. That was one of the first areas of instrumentation to give way to the embedded methodology, and you had the implementation of what's called on-chip emulation or in-target probes, where you have access to the the debug facilities on chip, also known as on-chip debug or OCD. Of course, with the structural test methodology, if you have access to physical test points, you might be familiar with in-circuit test. But as the circuit boards become more dense, the possibilities for physical test points and probes becomes diminished, and that gave way to what we know as boundary scan, which is another form of embedded instrumentation. And finally, more sophisticated, if you will, instruments are becoming available on-chip oscilloscopes and logic analyzers, on-chip bit error rate testers, and so on, ultimately leading to, in some cases, such as the low-cost test implementation at TI, access to reduced pin count testing for ICs themselves. So we'll stop here for a bit and talk about JTAG. So JTAG is really central to most of the embedded instrumentation that's available today. Not sure how familiar the group is generally with JTAG, but I'll just take a moment to introduce it. JTAG, formally, it's a word that describes or names the group that originally wrote the original boundary scan specification. Initially, that was a draft that eventually seeded the 1149.1 working group of the IEEE. In more informal use, JTAG is used to refer to that specification or to the 1149.1 standard itself, to the various progeny of 1149.1, and we'll talk more about some of those cases shortly as we continue the presentation, or in fact just to the standard test access port in isolation or in association with some functionality other than boundary scan, on-chip emulation or on-chip debug, for example. I've included a couple of figures to give those that aren't familiar with JTAG a little bit of an idea of what it is. One of the key features of JTAG is it defines a 4-wire test access port, a synchronous port that provides, of course, a clock for timing, a test mode select for controlling the state of the machine according to the state diagram that's shown at right, and a simple serial data input and serial data output, TDI and TDO. So in combination, those bring data onto the chip to access various instruction and data registers to implement the test or other functionality. And of course then there's a TDO to bring data off the chip. One of the things that's illustrated here as a predominant feature of 1149.1 is the boundary scan register. The boundary scan register is simply a shift register that intervenes at the boundary between the non-test pins, the system pins as they're called, and the internal logic that they feed or are fed from. And in effect then, that gives us a set of virtual test points that get placed onto the printed circuit substrate wherever that IC is placed. We'll talk a little bit then in the embedded instrument context about internal JTAG. Internal JTAG is a new standard for embedded instrumentation based on JTAG that is just closing its balloting process. So it should, we anticipate, within the next 6 months at the outside, be ratified as a standard. In fact, I think it's going to be reviewed in August, and so it might be approved as early as August of this year. IJTAG defines instrument access and connectivity that's abstracted from the instrument operation and procedures. And it does this by way of defining 2 new languages, the instrument connectivity language, which describe how the instruments are connected through a network back to the top level access, which is by way of a JTAG test data register. The procedural description language then describes procedures that are defined in terms of the instrument interface. And so those instruments can be, instrument procedures can be defined according to that IP block, regardless of which chips it gets placed on, in what quantities, or how they're connected back to the tap controller. A couple of examples of instruments that you see here are MBIS, memory BIS. They could also be logic BIS. They could be any sort of temperature monitors, voltage monitors, any sort of instrument that you can imagine, and we talked about several other categories earlier. All right, so moving ahead then, we'll talk about non-intrusive board test. We'll look a little bit at the what, why, and how of non-intrusive board test. The emphasis, as I said earlier, being on less probes and more coverage. What does all that mean? So we'll start with NBT as defined as an emerging test technology that integrates several complementary test technologies, and the purpose being to restore the test coverage that's lost when we lose physical access to printed circuit boards, the ability to probe the printed circuit boards. Boundary scan test is a core capability that's implemented for structural test, shorts and opens testing, if you will, an alternative to ICT, if you will, and we'll talk more about that. Other elements that are involved are processor control test and various sorts of built-in self-test, including what we call FPGA-Controlled test. We'll discuss all of those. The latter two, PCT, for example, brings in an element of functional test, providing, for example, at speed operation, and the built-in self-test methods deliver an aspect of performance test for test of your margins. This reference is from a white paper that offered, and it's available online as well if you click through the link. So why is non-intrusive board test needed? I'm sure really I don't have to tell anybody these days. We're all living these dreams or nightmares depending on which side of the coin you're on. Ever finer pitch and higher density interconnects leading to just the inability to physically get enough probes onto the circuit to test all of the nets that are on the board. Of course, we have blind and buried vias, as illustrated here. Quite obviously, if you have blind and buried vias, you can't probe the vias, so you have to bring those out to test points. And of course, the reason that you have blind and buried vias in the first place because you have a high-density circuit, and so you don't have room for test points. BGAs, who doesn't have BGAs on their boards these days? I was talking to Richard earlier. He's got very large boards, but he's still got BGAs on the boards. Heat sinks, of course, provide interference for physical probing, conformal coating where that's required, depending on your environmental concerns. AC coupled nets, we talked about SerDes or high-speed I/O. That's all based on differential and AC coupled nets. That leads to complication for probing. And just generally then the high-speed serial I/Os. The illustration that you see over here in the lower right-hand corner, if it was fully implemented, it would have a set of I patterns that's associated with it that on the right-hand side show a more or less open eye, indicating that there's no interference from the test points of probing in terms of the signal integrity on that pair. But as you add a test point, you get compromised signal integrity, and of course as you probe, even more so is your signal integrity compromised. In terms of, so that covers the less probes aspect of it. In terms of more coverage, increasingly folks are looking for more than just conventional structural coverage. As the functionality becomes more complex, higher speed, there's a higher concern for functional and at-speed testing and performance testing. And functional testing can deliver that to some degree, but with a level of coverage and particularly diagnostics that is troublesome, and especially in terms of the level of engineering effort that's required to deploy high coverage, high diagnostic functional test at the system level. So embedded instrumentation can come in and of course pick up your structural testing, what INEMI calls the PCOLA, presence, correctness, orientation, aliveness, alignment. Embedded instrumentation can also come in and pick up, of course, your interconnect, shorts, opens, and quality, which are also structural aspects. But beyond those, going into functional testing or functional coverage, we have interest to cover specific functional features on the board and to do it at speed. And beyond that, we have an interest in measuring or testing the margins of the circuit. Bit error rate we mentioned several times. That's one that features prominently in any sort of high-speed I/O that's based on SerDes type technology. Again, there's a reference to INEMI there that sources the scoring guidelines for PCOLA. Over here in the figure, there's kind of a representation as you climb up this stack of using boundary scan, for example, for structural test, what we call processor control test for functional test. That's a way basically of implementing functional test from the bottom up instead of from the top down, which is the conventional functional test methodology. And similarly, for performance, we have tools such as high-speed I/O test or FPGA-Controlled test, which employ the embedded instrumentation for performance or margin testing. For example, one of the things that we've done quite a bit at Asset is the system marginality validation, particularly based on Intel silicon. They implement a methodology that they call interconnect built-in self-test, which is an embedded instrumentation methodology accessible through JTAG that provides for physical layer testing by way of JTAG-controlled pseudorandom bit streams and on the receive end pattern checking. Sometimes that's done in a loopback fashion, and it can also, if the chips support it, can be done in a point-to-point fashion where you have the transmitter on one chip and the receiver on a different chip, what's sometimes called a master-to-master methodology. So in terms of the further definition of non-intrusive board test, kind of what is it at the how level, how do you do it? We've mentioned all of these in turn, and I'm not going to trouble you to read the detail here, but there's a range of methodologies and technologies available, starting with IJTAG, which accesses the chip-level embedded instruments through a JTAG network, the high-speed I/O validation, which is the BERT-like testing that we talked about, boundary scan for structural testing, processor control test for sort of bottoms-up functional test, and FPGA control test is a way that you can basically take the FPGAs that you have on board, and instead of loading them with their mission circuits, you can load them with circuits that are specifically intended for a test purpose. Since the FPGAs are reconfigurable, you can do that on a temporary basis, load up the test circuits, run the test, and then load in the mission circuit to move on to system test. Similarly, with processor control test, what we're talking about is running software that's not implemented at the system level, but running software that's implemented at a bottoms-up level, software that's specifically for the test purpose, and that doesn't, quote-unquote, just operate functions of the board, but is specifically targeted at achieving very specific test objectives. For each of these methodologies, there are an array of standards and sources for these. In the IJTAG arena, there's 1500 and 1687, which are both chipped embedded instrument standards. Moving on to boundary scan, there's a wide variety of structural test methodologies, and in-system programming is another thing that I should mention, which leads then, of course, directly into the FPGA-Controlled test methodology. And with the processor control test, you're looking at, of course, JTAG, on-chip debug, what are called debug access ports, extended debug ports, and the like. The software-based instruments that are implemented through the processor control test are used for testing a wide variety of interfaces that you have on your circuit cards. Various sorts of interconnect, QPI, DMI, PCI, Express, which I'm sure everybody's heard of, and so on. And final mention here, at the end you'll see SMBus. SMBus, which is an I2C based methodology, and similarly SPI, the serial peripheral interconnect, are another means of accessing on-chip instruments, both in the processor control test and FPGA control test environment, but also for boundary scan. You can use boundary scan often in a master chip to access an SPI feature or an I2C feature that might be in an off-board voltage or temperature monitor or the like. All of these links are also clickable. Hopefully when Gary generates the PDF, they'll all be clickable, and you can go through here and learn more about each of these standards. That's courtesy of a Standards Corner page that we have on the Asset Intertech website. We're going to dig just a little bit deeper here, talk a little bit about boundary scan. I guess we're not going to unmute here, but we gave a little bit of an overview of boundary scan earlier when we talked about JTAG. The main thing they'll emphasize, the boundary scan uses the JTAG port, what's also known as the test access port, to utilize on-chip resources to test interconnected circuits or the interconnections between circuits. In other words, it's a structural test methodology that's based on the virtual in-circuit test points that are made available through the boundary scan architecture. There's a slide in here which I won't belabor with a lot of detail, but hits on the meat of boundary scan, which is 1149.1 XTest, short for external test, and that basically provides the means to control chip outputs through the test access port and to monitor chip inputs through the test access port. And thus, if you imagine that there's a circuit on the right-hand side that's connected to this circuit that's on the left-hand side, you drive outputs to inputs and you can test across the interconnects between those two chips. The detail here talks about kind of how you access the state machine and the register in order to do that. But that's a lower level of detail that we need to go through right now. There's a little bit of a case study here, which again I won't belabor, but it's very relevant to our NBT topic because basically here on the QPI, which is an Intel Quick Path Interconnect bus, there aren't any test points. QPI is a very high-speed chip-to-chip bus. No test points are allowed, or at least that's certainly the preference in most cases. And so you don't have any means to test the interconnections between these two very dense BGAs except through boundary scan. And kind of the case study details how boundary scan, in fact, was able to detect structural defects under the BGAs where this QPI boundary scan methodology had to be implemented. Detailing processor control test a little bit, basically any processor that you have on your board today is going to have an on-chip debug port, typically called a JTAG debug port, or might be called a BDM or an ITP or an ODP or a DAP or an ITP. There are all sorts of descriptors for these things. But basically there's a port. Usually it's JTAG based at its core, although it has some additional interconnect. Access to the reset pin is especially important, so you can take control of the processor as it exits reset. Those debug facilities provide what's called run control, the ability to start and stop the CPU, the ability as well to read and write registers within the CPU, or in fact through the CPU read and write to I/O and to memory that the CPU has access to. And then finally to download software test code and run that test code. In the PCT context, those test codes are optimized for the manufacturing test purpose. So it'd be nice if I had some animation here, but basically the way that PCT works is you can think of this entire diagram as being dark to start. And when you power it up and you take the CPUs out of reset, you take control of the CPUs through the processor control test methodology. You load them up with reads and writes to go out and access the interfaces to other chips. For example, out here to the platform control hub. And by doing so, you access the interconnects, test the interconnects, and you also access interface function and a certain amount of function that's in those chips. You basically keep going progressively, extend your sphere of influence, starting at the core of the processor, moving out gradually until you've run test code that lights the entire diagram up in green. Now, this is different from the conventional system functional test in the sense that you don't have to boot an operating system. You don't even have to boot a BIOS. You essentially can access these test codes as the CPU comes out of reset. That basically takes the functional test burden and shifts it off somebody that has to be familiar with the system function and shift it on to a test engineer that knows the components and how they interface together. What do we use it for? We use it for test and debug of non-booting boards, including boards, as we said, without a BIOS or without the ability to boot. It's also used for fast flash programming. It provides for faster functional tests because you don't have to boot the boards. And it also provides for a certain ability to check your BIOS as a hardware and software validation task. Next, we'll talk a little bit about FPGA or FCT, FPGA-Controlled test. FPGA-Controlled test is somewhat similar to processor control test, except in the sense that it's a bottom-ups method, but it's focused on FPGAs. So think of the FPGA as being dark. You power it on. Instead of loading it with its mission function, you load it with test functions. Again, you don't have to have the system software, firmware code that controls the FPGA. In fact, you can implement FCT methodologies before one line of Verilog has been written for your FPGA. In doing so, again, you can go out and you can test the interfaces to other chips through this methodology. This shows a variety of different instruments that you might implement through such a methodology. I'm not going to read them all to you here, but just a couple of examples. Instruments that test your memory interfaces through to instruments that do digital pattern generation and pattern capture to fast flash programming. JTAG, as we know it, is basically one tap that provides access to many non-intrusive apps. TAP again means the test access port. The various non-intrusive apps that we're referring to include boundary scan test, processor control test, FPGA control test, and other embedded instrumentation, as we've discussed. Again, I don't want to omit in-system programming. In-system programming is a very key feature that's provided as sort of a core facility for boundary scan test, and also provides the means to implement the FPGA control test. As well, JTAG, the one tap, provides access to many non-intrusive benefits. Going to a lower cost tester that's not based on physical access provides you with a smaller capital investment, minimal fixturing. The higher coverage and the lower level diagnostic facility gives you a fast time to actionable diagnosis. Of course, the test development is highly automated. Reviewed most of that, so I'll, in the interest of time, move ahead. Another thing to consider is reuse across the life cycle. One thing that we haven't talked much about, but it's worth emphasizing, is that intrusive test methodologies are inherently not life cycle portable. You can't take the wafer prober that you use for chip test and reuse it at the board level, much less at the system level. You can't take the in-circuit tester that you use for board structural test and use it in the field. But the non-intrusive methodologies based on embedded instrumentation can be deployed throughout the life cycle of the system. The same instruments that are used on the chips, accessible through the JTAG port, are likewise accessible when your system is in the field, and you can take the information that you gather from those later phases of life cycle and feed it back to improve your incoming quality as you progress through the life cycle.